Okay, so continuing with our rigid transformations, we're going to talk about a composition. And a composition is nothing more than a sequence of these transformations. Two or more of the transformations performed in a sequence. So you have to make sure that you do the order correctly because order will sometimes matter. And that is really about it, following the same rules and same mappings that we've had in the past. So here in this first example, we're saying they're describing here that they want to reflect over the line M, and then they want to rotate 90 degrees about E, point E. Now, obviously, there's no grid here, so it is an estimate, but if I were to reflect over the line M, I would take E and it would be reflected over line M. I would take G and it would be reflected, and then F would be reflected. So my first transformation would look something like that, and obviously, it's just an estimate. Now, if I wanted to rotate now 90 degrees, you've got to remember that we are going to be rotating that direction counterclockwise. It's 90 degrees, so we assume it is a positive measurement. So with that, just thinking about 90 degrees, F would be 90 degrees this way. So that would be F double prime. G would be 90 degrees this way. G double prime. And then E double prime didn't move because that's what we were rotating about. So just connecting my dots, and that's what my image would look like. So my final composition should hopefully look like that orange drawing there. Now, if we were to do it out of order, so picture this, right? If we were to do it out of order and we rotated, so this is the correct image. I'm going to go ahead and erase that. And if we were to do it out of order, we would rotate first. Okay, if we did it out of order, rotating would put F approximately there, G approximately there, and then, let's see here, F, so it looks something like that, okay? So this would be G prime, this would be F prime. And then now if we reflected it over the axes, G would be over here, G double prime. E double prime would be over there, and then F double prime would be over here, and that is clearly in a different location as my previous correct answer. So that's why order definitely matters here as we work on these. We got to make sure we do it in the right order to where we get the right final composition. Now here, so just being able to look at it and describe it and understand what's going on, following the primes, hopefully we know that if my original image is my pre-image, this would be my first transformation, this would be my second transformation. So judging by this reflection, if I, again, if you connect the points, right, F, F, G, G, we're starting to see that parallel, that bisector. So we have a reflection. So the first thing we did was reflected over line M. And I'm just going to say reflected over line M. And then we rotated. Looks like we rotated this direction because we have a point of rotation of G. And then we went 90 degrees, it looks like, because H prime went to H double prime 90 degrees. And that is a negative direction because that is clockwise. So then we rotated, let's see, rotated about G prime negative 90 degrees, or you could have said 270 degrees positive would have been the same effect. So just being able to describe what's going on there. Here, we started off in this first move a pre-image, first move, second move, and it looks like we rotated 90 degrees. We went here to here, so we went 90 degrees and a negative 90 or a positive 270 degrees. And then we ended up doing a reflection, right? We ended up reflecting, so then we had a reflection. So you can see here in these two examples, depending on which order you do, we had the same transformations. They were just done in a different order. So order is going to matter. Let's see here. Here's some basic transformations. What I did is give you an entire list of what we've been doing over the course of the last several days. So good information to have on a cheat sheet, a note taker, something to help you out, because when they're, these mappings make things extremely easy. And then here doing the composition on the coordinate plane. Now it gets a little bit more technical, but again, we're going to use these mappings and it'll get us through. So it says, consider the sequence. First, we want to reflect over the x-axis, and then we want to rotate 90 degrees. So we have, the first thing is my pre-image. This is my pre-image. This is my first transformation where I reflected over the x-axis, and then now I want to rotate 90 degrees. So I take, here's my first, and I want to get to A double prime, I want to get to B double prime, I want to get to C double prime, and I want to get to D double prime. And this is my transformation. So my xy becomes negative yx. So here's my y, it would be negative, so negative times negative 4 would be a positive 4, and then my x would just remain the same. So as I do that same thing here, my, again, negative would become a positive 4, negative 1, negative would be a positive 2, negative 2, and then again, negative would be a positive 2, negative 4. And those are going to be the points that I'm going to end up graphing over here. So let's see here. 4, negative 3. Oops, one too many. 4, negative 1. C, and then D. There you go. There's my composition. There's my second transformation in there. So that's what it would look like. So here they're saying, what is the coordinates of the vertices of the pre-image given? Given, they reflected over the x-axis and then they had a translation. So we have to reverse all of that. How do we do that, right? The first thing I could reverse is I could say that my xy is x minus 5, y minus 1.5. That got me, this was my first movement. So if I wanted to reverse that, or this is my second movement, sorry, I need to take that and I would have negative 4 instead of minus 5, I would add 5. I would have 2 instead of minus 1.5. I would have plus 1.5, and that would reverse that. So it looks like W prime should have been 1 and 3.5. And then so I reflected over the x-axis, and then we know that when we reflect over the x-axis, we're going up and down. So the only thing that changes is the value of my y, the sign of my y. So it would stay 1, and negative 3.5. So I could work through that, and I'll just pick z here. So again, z would be negative 2, but we have to reverse that. So instead of negative 5, we're going to add 5. Y is going to be 0.5, sorry. 0.5 plus 1.5. So then my z prime would have been 3, 2. And again, as I rotate or reflect over the x-axis, I have z would have been 3, -2. So these would have been my two starting points. And we could, again, do the same thing with all of those points. But just working backwards, trying to see where did we start off from. All right, so here, looking at this figure, BCD, don't know what the figure is other than it's a quadrilateral, was transformed using the composition. We went over the x-axis and then we translated 2, 2. This is basically saying a vector of 2, 2, right? Or we would have said x plus 2, y plus 2 would have been the translation. If B on the pre-image lies at 3, -4, what are the coordinates of B double prime on the final image? So we start here at 3, 4. B prime is going to be reflecting over the x-axis. That was the x-axis again. My x remains the same, and then my y turns the opposite sign. So x remains the same, 3, and my y would be a -4 instead of a +4. And then for B double prime, I would have 3, and then I'm going to add 2 for my translation. And then I have -4, I'm going to add 2, and then therefore B double prime should be equal to 5, -2. So that would be the location of B double prime after my transformation. Okay, looking at 5, this sequence. We rotated the sequence of transformations, rotation about the origin 90 degrees, and then reflecting over the x-axis is applied to this image to produce my composition triangle. If the coordinates of y double prime are 3, 0, what are the coordinates of the original y? All right, so y double prime is 3, 0. And we want to get to y prime. The first thing we have to do is reverse the reflection over the x-axis. And we just said several times that over the x-axis, my x value remains the same, but my y value becomes the opposite sign, which there is no opposite to 0. It's just 0. There's no positive or negative. So that made that easy. And then getting to my original y, I reflected over the x-axis, rotated 90 degrees. So I would have to reverse that. So again, this would be -3 and then 0. So it looks like my original location should have been, because I have to reverse these, right? Y, because this is my y value, this is my x value. It should have been 0, -3 is my original location. Okay, so just having to reverse in the reversed order. What rule describes the composition of transformations that maps along the way? What did we do here? Let's just think about it. It looks like when we went from E to E prime, it looks like we just rotated that entire object. So let's think here. We rotated, is that positive, negative? Let's go in this direction. We rotated 90 degrees about the origin, right? About the origin. And then it looks like when we went from there, we ended up just doing a translation and we moved everything. It looks like we, I'm just going to write it in vector form here. We translated 1, 2, 3, 4, 5, -5, and then we didn't move up or down any, so my vector would have been 0 for up and down. So we translated 5, 2, and we could have also written that as x minus 5y, showing my mapping for that. And then analyzing this pre-image in example 7, what are the vertices of the final image if we did that and we did that? So first of all, this is x minus 1, y minus 2. That's my first translation. And then we are going to reflect over that line. So let's see here. X minus 1, which would bring that back here, right? A, 1, 2. So this would be my new A, my new D, my new C, my new B. Okay, so there's my new image. And then we're going to reflect over y equals x. And that line is this imaginary line right here. Y equals x. A little bit more difficult to see, but as we reflect over, there is a mapping for it, but what I'm going to do is just say, hey, if I am this far away from my line of reflection, that would put B double prime right there. If I am this far away from my line of reflection, that would put C double prime right there. D happens to be on the line of reflection, and then A would become over here, A double prime, because I am that far away. So there is my new location of B double prime. A little bit, when you start seeing a bunch of stuff on top of each other, it becomes a little bit more difficult, but using different colors helps. So with that, there you go. There's looking at those compositions. Continuing on, let's see here. Did we miss anything? Composition. Glide reflection composition is a translation followed by a reflection in a line parallel to the translation vector. Okay. We'll get some couple examples of that. So with that, let's see. Let's see, we did those examples. Here, if we just look at this one, check. Triangle JKL has these vertices, and determine the coordinates of the vertices of the image after a translation along 0, 4 and a reflection over the y-axis. Okay, this is going to be the y-axis trans mapping. Here, this is x plus 0, y plus 4. So we'll just take one point. Let's take L. And L is 5, negative 3. And then L prime would be the first translation. So that would be 5 plus 0, and then negative 3 plus 4. So L prime is 5, 1. And then we're going to map that to L double prime, and we're going to change the sign because it is reflecting over the y-axis, right? So we're changing the sign of our x coordinate. So it would become negative 5, 1. Negative 5, 1. So that's just how we would look at all of those points. But again, just following it in order. And here they've given us some compositions. And to look at this, they have rotated about the origin 180 degrees. And then they have done a translation where they have gone back and then up. Looking at that. So we've done some examples like that. And let's see. Moving on. Reflection about parallel lines. Just looking at it, see, it says reflections and parallel lines. A composition of two reflections and parallel lines can be described by a translation. So if you look at this, if we have two reflections, we reverse the, think about these 2 points. They reflected and then they reflected again. So it looks very much like my original image just translated over to this location. So two reflections like that can look like a translation. So that's what they're talking about there. And let's see. Reflecting over two lines. A composition of reflections and intersecting lines can be described by rotation. So it does appear to look like a rotation instead of just a reflection and a reflection. It looks like we just rotated. So just some characteristics of multiple actions, and it takes practice to see these. And now as we continue with symmetry, nature loves symmetry, just going to say. Let's see here, for this, we have line symmetry. A figure in a plane has line symmetry if each half of the figure matches the other side exactly. So thinking of symmetry as like a butterfly, things that fold in half and fold on top of each other. And then when a figure has line symmetry, the figure can be mapped onto itself by reflecting in a line called a line of symmetry. So for example, if I were to take this pentagon here and I were to fold it in half, along that line it would fold on top of itself like a reflection. So they're trying to say, hey, technically we have 5 different locations that we can do that from, and we could have created that reflection, so that line of symmetry, so it has 5 lines of symmetry. Where this object over here, this is a scalene triangle, and no matter where I try to draw a line, I'm not going to be able to have it fold on top of itself. So there are no lines of symmetry in that image. So just thinking about it, visually looking at it. Determine whether each figure here has a line of symmetry. If so, draw the lines of symmetry and state how many. Well, this is a rectangle. I know that if I fold it in half this way, it should fold on top of itself. If I fold it in half this way, it should fold on top of itself. So it should have 2 lines of symmetry. Where I have here, this looks like an equilateral triangle. So I have 1 line of symmetry, I have another line of symmetry, and a 3rd line of symmetry that I could fold. And then I would say that this trapezoid here, if I folded it like that, no line of symmetry. If I folded it like that, no line of symmetry. If I connected my vertices, no line of symmetry. So that is no line of symmetry. Okay, now rotational symmetry. If the figure can be mapped onto itself by being rotated less than 360 degrees about the center of the figure, so that the image and the pre-image are indistinguishable. Okay, so I think of rotating this. If I were to rotate it 90 degrees, it would look like itself. Every 90 degrees, it would fall back onto itself. So it would look like a diamond shape. And that would be, they would look at this and they would say, how many times? That would be my order, which is 4. And then my magnitude would be that 360 degree rotation divided by 4. So my magnitude is 90 degrees, which means every 90 degrees when I rotate it, it looks like itself again. It's indistinguishable from the pre-image. Okay, so that's what they're talking about there. And let's see if I had this is always hard for me to draw, but a hexagon. If I were to rotate that around itself, technically each one of these sides, as I rotated it, I could rotate it an order of 6. So 360 degrees divided by 6 is 60 degrees. So every 60 degrees, it's going to look like itself as we rotate around. So my magnitude is 60 degrees for a hexagon. So got a little bit ahead. Here we go. Point symmetry is just saying that it will rotate 1 time around. 180 degrees. Point symmetry. So a definition, understanding the difference between the types of symmetry. And then again, nature loves symmetry. And it really depends. Determine whether each figure has a rotational symmetry. And I would say that depending on how you look at it, if I were to cover that up, I could say that leaf has symmetry. I could have 1 line of symmetry, or point symmetry, I guess, because I can cut it in half. Not point symmetry, just line of symmetry. But it depends on how you distinguish that, and you turn around and maybe you interpret that as technically that point right there will not cut in half. It would not fold onto itself. It just depends on how you want to examine the image. This image, I have line symmetry. I have line symmetry at the petals. where I can fold it in half. And I also have line symmetry in between the petals where I could have folded it in half and come up with it. So I believe that there are actually 8 lines of symmetry there, 8 rotations. So, think about 360 divided by 8, it gives me an order of 8, a magnitude of 45. So every 45 degrees, the petals would look like its original pre-image. And here, this is 4. Looks like if I rotate it 4 times, I'd be okay. So I could say that it does have rotational symmetry about the center. So just thinking about it, again, we did the 4-sided before, and that would be a magnitude of 4. So 360 degrees, an order of 4, a magnitude of 90 degrees. So just thinking about these kind of things. And let's see here, draw below are several objects that you might find around the house. Determine whether they have rotational symmetry. Rotational symmetry about the center. Definitely can rotate that orange slice. I cannot rotate the pair of scissors. I would say that I would argue, depending on how you visually look at it, if that was a TV screen or an iPad, if you looked at the shape of it, you could say, I can rotate that about the center, but maybe you identify and you say to yourself that because of the color differences, it would not look the same. So it just depends on how you examine those images and how you're thinking about it. So I will try not to have obscure items on our information like this, but definitely it depends on how you can justify it to yourself along the definitions. And then here finally, talking about our order and magnitude. And then here, talking about determining the magnitude again. We have an item here that's a pentagon. It has 5 sides, so it does have rotational symmetry. Order of 5, and then 360 degrees divided by 5 is 72 degrees. This is a trapezoid with no rotational symmetry, so it has no order or magnitude. This is a parallelogram, which by definition is, it will have rotational symmetry because we can rotate it. It will rotate twice, and then it is 180 degrees. And because it's 180 degrees, we know that that is that point symmetry definition. And then we also have down here in our check a rectangle, which is a parallelogram. So a rectangle is a parallelogram, which also has, just like a parallelogram, rotational symmetry, order of 2, 180 degrees, and that is point symmetry. This kite does not rotate back onto itself, so it has no order or magnitude. And this equilateral triangle should have rotational symmetry. It has an order of 3, 360 degrees divided by 3 is 120. So there you go. That is rotational symmetry tacked on with compositions and transformations, and as we will dive more into this in our assignment today.